Swayam Prabha. Digital India. Educated India.
So good morning everybody. Shall we get started? Yeah. So we are going to continue from where we left in the last lecture of the evening. I will do a quick recap of what happened in the last class. Before that, I would like to know whether you have had a chance to look at the tutorial sheet. So the tutorial sheets have been uploaded. Did you go through the problems? How many of you were able to go through the problems? Maybe not solve it yet, but okay, so you have looked at it, some of you, good. So, yeah, please do attempt to solve the problems very seriously. They will give you more insights about the questions that we have left not completely answered. Okay, so I'll recall the setup. We have applicants and posts, and we have applicants having preferences. And posts not having preferences. So we call this the one-sided model, and we allow strict but incomplete lists. And we would like to compute a matching which is popular and a matching is popular if there is no matching more popular than that. So we have seen that popular matchings may not exist. When they exist, they form a very nice solution because no majority would like to deviate from that matching, and therefore we are interested in answering the question, does there exist a popular matching? We have already answered that question by defining what is, for every applicant A, its F post, which we will call as FA. And what is FA, to recall? Yeah? Yeah, to you. Yes. Yeah, the first preference given by the applicant. And we also defined S of A. What is S of A? Somebody else? Yeah? What is candidate preference? Yeah, but how do you decide what is your S post in your preference list? Yes, do you want to help? So it is, we'll recall that it is the most preferred post which is not an F post, not an F post for anyone. So recall that we said we will look at the preference list and delete all posts which form an F post for anybody else. Your own F post will not get deleted because it's your own F post, but from your second choice and onwards, you will delete posts which are not your F post but possibly somebody else's. Whatever remains after that as the most preferred choice is called your S post, right? And then we have a reduced graph G prime where every applicant adds exactly two edges, one to its F of A, the other to its S of A, and we said that if this reduced graph has a matching that matches all the applicants, then that matching is popular. And then we also said that if you just subject this reduced graph to any maximum matching algorithm, it may not have the property that every F post is matched. So you may have to do some post processing by looking at the matching and then changing some of the matched edges. So we know an algorithm, so an efficient algorithm to decide whether G admits a popular matching and compute one. And we were at the stage where we would like to ask, can applicants cheat or misreport preferences when they have information about the preferences of other applicants, and they know that the central authority is going to select any arbitrary popular matching, and we would like to develop, we would like to study the structure of the problem. For this, we said that we are going to talk about what is a switching graph. So, can somebody recall what are the inputs required for us to even construct the switching graph? A matching, but any matching will do? A popular matching. So, we would like the instance G, but using the instance G alone we cannot construct, we need a popular matching M, and we spoke about that because the popular matching must match every applicant, and remember some applicants may have been matched to their last resort dummy post. We had also done a pre-processing that does not change the status of the instance, that is from being admitting a popular matching to not being, or vice versa, it does not change anything. So, we can safely say that if you look at any applicant, there is something called M of A. What is M of A? The post that it is matched to in the matching M, and this can be only from two things, either it can be F of A or S of A. So, we can safely call OM of A the other post that A would like to get matched to apart from its MA, right. So, if MA is FA, OM of A is S of A, and if MA is SA, then OM of A is F of A, right. So, this because we do not want to say what is it and we do not know, therefore, we will just call it OM of A, the other post that it will get matched. So, it is very much dependent on this matching. So, we said we would like to construct a switching graph, and we have also said exactly how to construct the switching graph. We will do this for an example with a so, why are we constructing the switching graph? Does anybody recall? Yeah, why are we constructing the switching graph? What is ranks of matchings? What is popular does not require us to construct a switching graph exactly, because we can execute that algorithm, right. We just said construct the reduced graph, compute a maximum matching, and then post process it to do something, but you are on the right lines. There is something else to do with the ranks. What is it to do with ranks? Yeah, so we would like to answer this question, that if we look at an applicant, what all posts does it get assigned to in different popular matchings of this instance. So, this problem can also be called as computing popular pairs. So, popular pairs is just a set of edges such that, so popular pairs is a set E prime, a subset of E, such that AP belongs to E prime if there exists a popular matching M such that AP belongs to M. That is, A gets matched to P in some popular matching, then we will call it a popular pair. And we have also observed that we call them the underlined post for an applicant. We said that the underlined post can either be its F post, or it has to be some other post which is its non-F post, but it is its S post, because that is the characterization of a popular matching. So, in particular we said that it cannot happen that 2, 5, then something 7 and so on are underlined. One of them has to be F, the other can be some other post, right. This is what we had seen. And why would we like to identify this? Because we would like to know that if for an applicant it always gets matched to its F post in all popular matchings, that is his only underlined post is P1, then he better not do anything about cheating, because anyway every popular matching matches him to P1. So therefore it's best for him to report his true preferences. On the other hand, if he is an applicant of the type A1 and P5, maybe he is interested in cheating because there is a popular matching which matches A1 to P5, and he may want to force the modified instance to have the popular matching match only A1 to P1, right. So this could be his goal. It could also be the case that he is only getting matched to his S post always. So we also defined applicants of the type that is just obvious from this popular pairs AF, AS and AFS. So very conveniently they are named as applicants who will get always matched to their F post, applicants who will get always matched to their S post, and applicants who sometimes get matched to their F, sometimes get matched to their S, right. So now we should quickly find a popular matching in this so that we can construct a switching graph, right. So A1 has P1, A2 has P1, A3 has P2, A4 has P4, A5 has P5, right. Yes, sorry, P4. So these are the black edges which are the F post edges. Every applicant will also have an S post edge. So for A1, A2 it is P2, is that right? Please correct me if I make any mistake. So I will just draw the S post edges in yellow. No, it is not P2 actually, it is P2 won't be there, so it is P3, right. So for both of them it is P3, A3 it is P6 and A4 and A5 it is P5, right. So this is how the picture looks like, the reduced graph, and as you see there are multiple maximum matchings, and one of them if we pick up it will be we will just call that the popular matching. So we will say A1 P1, A2 P3, A3 P2, A4 P4, A5 P5, right. So this is one popular matching. There are others, but I have just constructed this I will call as M. Now how does one construct a switching graph? What are the vertices of the switching graph? The posts, right. So I will just draw P1, P2, P3, P6, P4 and P5, right. Now this is the set of posts that I have drawn. I would also like to draw edges in this graph, and the edges we said are determined by the matching and its OM of for every applicant, right. So the edges of this graph are actually applicants in our original instance, and we want to draw an edge from a post to another post. So can somebody tell me whether there is an outgoing edge from P1? Okay, what is that edge? P1 to P3, right. That edge is there because A1 is the matched applicant and it likes to get the OM of that is P3. So this is A1, right. This edge is labeled as A1. What about P3? Is there an edge? Yeah. So P3 has an edge which is like this. Yeah, this is labeled A2. Now we see that A3 is matched to P2, therefore we will have an edge from P2 to P6 which is labeled as A3. But from P6 we cannot draw an edge because there is no applicant which is matched to it. So therefore it does not have anybody to go out. Is this clear? Is this clear to everybody? How are we drawing these edges? If there is any confusion, please ask, because all of the strategy that we will develop is based on this. Yeah. Okay. So then what about P5? Where should I draw the edge? A4, right? And then there is also this edge. So P5 is actually, P5 to P4 edge is labeled as A5. and this is A4, right. So this is how our switching graph for this example looks like, right. Okay, can you, so we have already observed that there can be vertices which are, so a vertex or a post P can have no outgoing edge, and such a post P must be an S post. So we will also call this as a sink. This is typically called a sink, that is, it is a vertex from which there is nothing to go out, right. So it is a sink vertex. So here P6 is a sink vertex, there is no other sink vertex, right. So there is also some more property about this, any edge of this graph. So let us say there is an edge from Pi to Pj. What can we say about the posts Pi and Pj in terms of their F and S nature? So can it be that both of them are F posts, both of them are S posts? So exactly one of them is F, the other is S, right, because that is how we have drawn the edges. So all edges are either going from an F to S or an S to F, right. This is a very simple graph. So in this example it turns out to be very simple in the sense there are just 3 components, but also you observe that these components, it need not be a connected graph, and it can have components, and we were asking how complicated can the components look like. For example, can I draw a structure? So this is the switching graph, so I will just, so this is for GM. This is typically called as GM, the switching graph. So for example, let me ask that can it look like this? Can the structure look like this? So what is wrong? So let me label the post. So it is called P1, P2, P3, P4, P5. So can it be, can I have the switching graph like this? Yeah, why can't I have? Not more than one incoming edge. Yeah. So what is wrong with this? There is something wrong, but we should identify what is wrong. So what does it mean to have two incoming edges? That there are 2 applicants who think that this post is your F. Suppose that post is an F post. There are 2 applicants who are matched to somewhere outside of F post, but they think that this is their F post and they would like to go there. So there can be vertices which have multiple incoming edges, but there cannot be a vertex which has multiple outgoing edges. Is that clear? So while multiple incoming edges is not a problem, multiple outgoing edges is a problem. So this vertex having 2 outgoing edges cannot happen, right? So this is not allowed, this is forbidden. So let us start drawing complicated structures with this property, that is every vertex has 1 outgoing edge. So you can have this, such a thing is allowed, right, because it can keep coming. Then maybe I will let it go out, then let it come in, and so on. So I can have this. Maybe I can stop at some vertex because I am allowed to have vertices which are sink vertices, right. But if I have this vertex as a sink vertex, immediately I know that this is S for somebody, right. Immediately this fixes that this is F for somebody. Similarly, this fixes that this is S for somebody. This is F, this is S, this is F, and so on, right. Okay. So now if I take a component, it seems to have, we are allowed to have 1 sink. Can you think of a way of constructing 2 sinks in a single connected component? So you can again have another structure like this, and you can have 2 sinks in the switching graph, but in the same connected component can you have 2 sinks? Maybe you want to try drawing so that you will see whether you can construct it, or if you cannot construct it, then we should ask. You need 2 outgoing edges. Yeah, so you should convince yourself that if you want to construct a connected component with two sinks, then you must have some vertex having two outgoing edges, but that is forbidden, right? So we know that if you have a connected component, we'll call this component a tree component because there is no cycle in this, but such a tree component must have a sink vertex, because if it doesn't have a sink vertex, then this also has an outgoing edge, then where does it go to? It cannot go on infinitely because the posts are finite, so maybe it comes back somewhere, right? So good. So there are sink, there are components which we will call as sink components. So sink components have, or every sink component has exactly one sink. So then the non-sink component is the one which has a cycle, right? Because it seems, so if we do not have a sink, we must come back, right? So again, so here we seem to have that there is only a cycle. So maybe if there is a cycle, there cannot be anything else. Is that correct? That is, I cannot have anything else attached to the cycle. It's a simple cycle and nothing else. This example motivates us to make that claim. So, okay, you seem to say yes, you seem to say no. Is there any other support for them because they are standing alone? Yes or no? So the question is if you have a cycle, should it always be a simple cycle and nothing else? So clear, I mean, I hope it is clear that you cannot have something like a cycle like this, right? I mean, you cannot have something inside the cycle, because otherwise it will have two outgoing edges, but that is not allowed. But this is okay, but still a simple cycle, there may be a simple cycle, but there may be something else, right? So you seem to think that there is something else. How? So tell me a structure. Cheating. Okay, but we are not even talking about cheating, but good, your observation is on the right lines. But what we will draw first is how complicated can a cycle component look like. So she suggests that there is a cycle, and then it need not be a 2 cycle, but then can it be a 3 cycle first of all? So if it is a 3 cycle, then we said that every edge is from F to S. So without loss of generality, one of them is F, then this is S, then this is F, then this is an F to F edge, but this is not allowed. Right? So the cycles are of even length. So this is also a nice property. So maybe there are bigger cycles, because in this example it doesn't happen, but there can be bigger cycles and you should construct them. So when I say Fs, it is just the nature of that post. It is not the name of that post. These are different posts. But what she is saying is that you have shown what is the OM for these people, but maybe there is another applicant who treats this as its F post and it is matched to his own S post, in which case you can have something incoming to this, right? So if you want to create something like this, then we have this A1, P1, A2, P3, this cycle. Maybe if there was another A4, not A4, A6, which also thought that P1 is its F post and it is currently matched to its S post, which is this. Then we will have A6 which will be having an incoming edge to P1, right? And you see this structure being created. Is this clear to everybody? So you can have things like this. Is it the case that only one such path can come into it? Not necessary, right? You can have many such things coming into this, because there may be multiple. I can just create A7, A8 and so on, and they can come into this. In fact, why stop here? There can be something which comes into this and so on. There can be a long tail below that, right? But now again we will ask, so this is a non-sync component, can it have multiple cycles? Can it have multiple cycles? No, again using the same logic that we said, it cannot have two sinks in the same component. If there is a cycle, there is exactly one cycle, and if there is no cycle, there is exactly one sink. So either the component is a sink component or it is a cycle component, and there is exactly a unique sink in that or a unique cycle in that, right? Also note that I cannot draw anything outside of this. I can again draw something incoming to this. Maybe there is also incoming to this, but I cannot draw anything outside from this cycle vertex, right? So therefore, every vertex participates in at most one cycle. It is the vertex in the sense the post. The post belongs to either a cycle component or a sink component. Any questions about this? Okay. Yes. Yeah, so the question is, what is the maximum number of incoming edges, right? How many incoming edges can you have for a vertex in this switching graph? So we'll say that a post is either an F post or an S post. So if it is an F post, then it cannot be left unmatched. Therefore, it will be the number of people who treat it as its F post minus 1. These are the incoming edges. If it is an S post, again it can be left unmatched, in which case the number of edges is exactly equal to the number of applicants who treat it as its S post, or if it is matched, then it is number of applicants who treat it as its S post minus 1, right? So it's very well defined, and you can easily tell what is the degree in degree of a vertex. Out degree is anyway 1. So it's a very simplified, nice structure. In fact, it is visible in here itself. You could have done all of this here. It makes things complicated, but it's there in this. It's nice to draw this out separately, which gives us much more clarity on what is happening. Okay, so every sink component has exactly one sink, and we also observed, so this is property 1, there is property 2, that every cycle component which is non-sync has exactly one cycle. Okay, so so now instead of looking at it as a small example, we should be able to think about it abstractly. So if I have a component which looks like this, which is a tree component, it can look fairly complicated. So immediately as I label this vertex as a sink, I will call it S. I will actually, instead of keeping on writing as S and F, I will label the red post as F and the non-red posts as S, right? Sorry. So does everybody see this? So I have some component which I have abstractly drawn. Once I draw this, you should be able to construct the preference lists of the applicants, right? And I will not do that, but we should be able to abstractly think about this as a component of that. Does anybody have any issues? How did I draw this? I just think of that I can label all of this as A1, A2, A3, A4. As soon as I label this and I label the posts, I can also construct the preferences. So if I label this as P1, P2, P3, P4, and this is S, but I'll call it now P5, P6, P7, P8, P9, P10, P11. Then there are so many applicants, and so each of them has an exactly one outgoing edge. So there are 11 applicants, and they have their F and S posts, but it is easily constructible, right? So if I choose this applicant, let's call this some A3. Just to understand, what is its F post? A3's F post? From this figure. So if this edge P3, P4, I am calling it the applicant A3, then what is A3's F post? But I said that I will call the P4, sorry, yeah, P4, and what is its S post? P3, and in this matching, what is it matched to? P3, so it is currently matched to P3. And why am I drawing a gap? Because I can write lot of posts in between, but what are the posts that I can write? Only the red posts. Right, I can write only red posts in between. For example, P7, P10, P11, P6, any combination in any order I can write. That doesn't bother me at all. So the instance is fixed, but I am not talking about that instance explicitly, right? All of you can construct that instance, and it is only one instance, barring the fact that there can be a lot of permutations that you can do in between, but those don't matter to us. Okay, so now what we will talk about is paths in this graph, right? So let us start with some path. So if I take this very simple path, which is P8, P7, P5, right? So I'll highlight this path. So this is the path P8, P7, P5, and I will say that so this path I will call it as T, because I cannot use P. So I will call this path as T, and I will talk about what I say is applying this path to this matching. What I will say is I am now going to apply this path. What do I mean by applying this path? Now note that I have very carefully chosen the path to end at the sink vertex. What does it mean by ending at a sink vertex? Now there is this applicant, which maybe I will call it as, so I will call these applicants A7 and A8, right? So can I actually make A7 get matched to P5? It is currently possible because so there is a current matching M, right, with respect to which you have drawn this switching graph. Now I am going to change that matching, right? So I would like to use this part to change the matching. So the M matching is determined by this. Does everybody see the M matching? If I call this applicant A1, A1 is matched to P1, A2 is matched to P2, A3 is matched to P3, and so on, right? So I will just have that matching. I would like to change the matching. So M prime is equal to M minus, so I will remove this edge which was A7 matched to P7. I am removing this, and I will also remove this edge A8 matched to P8. Right, so this is what I am removing, these two edges. If I remove these, I can actually get other partners for A7 and P7. What are the other partners? So it is using this path. So what can I do with A7? Where is another possibility for A7? So does everybody see this? This A7 is this applicant, right, on this edge. Remember, every edge is an applicant. So currently it is matched to P7. So why did we draw this edge A7? So this A7 is matched to P7. This is its other partner, which is P5. Is it possible to match it to P5? It is a valid match because it is S of A, and possibly it is also free currently, right? So therefore, because its P5 is a sink vertex, therefore it is a free vertex. Therefore I can match A5. So if I remove these two edges, then I can add A7 P5. As soon as I have made A7 unmatched from P7, P7 is free, right? Can I leave it unmatched? Technically yes, but if you leave it unmatched, there is no hope of getting another matching which is popular, because a popular matching must match every F pose. So therefore, you cannot get a matching which is a popular matching. So but I have already used this path. So therefore, there is also now a possibility of matching A8 to P7, right, because P7 has become free. So therefore, I will say A8 P7. So what I did, I removed the partners of two applicants A7 and A8, these two people, and I got them new partners. A7 got P5 and A8 got P7, right. So in this graph, what has happened is actually this, that these were the matchings in the original graph. A8 was matched to P8 like this. We are exploring this path, right. So we are starting at this vertex. We are saying that anyway it is free, let me match A7 to P5, and then this vertex becomes free, then I will match A8 to P7, right. So if I do this, what have I got? I have got another matching, that is for sure, because I did not violate the condition that two posts are getting matched to the same two applicants are getting matched to the same post, and vice versa. So I got a matching. I am asking, is this a popular matching? So I started with a popular matching. I did some small tweaks to it. The rest of the edges remain the same. Is it a popular matching? How will you check quickly if it is a popular matching? Good. So now she is saying that A8 has gained 1 and A7 has lost 1. Then you will get a popular matching. In this example it is correct, but in general this is not the correct argument. So we should ask, does this matching respect the properties that we asked for in yesterday's class? So we said every popular matching must satisfy some conditions, and if a matching satisfies these conditions, it must be popular. So what were the two conditions that we asked for? Yeah. What were the two conditions? Yes, I am asking you. Every F post must be matched. And every applicant should be matched to one of its F or S, right. So now is this property retained? For the remaining applicants, we did not change anything. For A7, we did change its partner, but we went to OM of A. So if originally it was a red post, it will become a non-red post, which is fine, it's S post then. Similarly, for A8 also, we went from a non-red post to a red post, which is fine, and thankfully we did not leave a red post unmatched. Now what does this amount to in terms of changing the switching graph? Because remember, the matching has now become M prime, it is no longer M. But will anything change in terms of this path P1, P2, P3, P4, P5? I mean, now remember that I have constructed this is a part of GM. Now I have another matching M prime. I am claiming that that is also popular because it satisfies the two conditions that I am interested in. So therefore it is popular. So I can also construct GM prime, right? And what is GM prime and how does GM prime look different in terms of GM? If there are other components, they are untouched because everything else for them remains the same. For this component, things do change. P8 becomes the new thing. In fact, I will draw exactly the same thing for everything else. So this is P1, P2, P3, P4, P5. These edges remain unchanged. So this is the graph GM. Then P6 also has the same kind of edge. In fact, if I look at this P7, it continues to have an edge from P9. But this part, and again P8, this continues to have an edge from P11. Nothing has changed, and this P10 continues to have an edge from here. Nothing has changed up for the rest of the people, but this, because I applied this green path has reversed its edges. Does everybody see this? because now P5, A7 is matched to P5 and its O M prime of A has become P7. Similarly, A8 is matched to P7, so its O M prime of A has become P8, right. So now this is a very nice trick, right, or that this is a very nice property of this graph, that is I can take paths, I can apply those paths. So this actually this operation is called M dot T. This is some notation that we use, and this we get another matching M prime by applying this path to this matching, right, and we get another matching, but the path was very carefully chosen. So I would like somebody to tell me another path which I can use and get another popular matching. So actually each one of you, why don't you write one path in your notebooks which you think, apart from this path, the T path that I have written for you, let us consider M only. We have already gone to M prime, but we will now consider M again and ask what is another path that I can apply. So everybody should write some path. There are multiple paths. We will see whether these paths are good, bad, are there some bad paths, is every path good, and so on. Yeah, so I think I will select, yeah, behind you, whoever is, yeah, that person, yeah. Can you please tell me one path that you have written? No, there is nothing about, you have to, you can observe this graph and tell me one path. See, you have to tell a directed path, you understand directed graphs, so therefore there is a directed path. You just tell me a path that you think is your favorite path, and we'll see whether we can apply that path. There is nothing about computing, right? I selected this path randomly. Yeah, so you select your path. Apart from this path, you have a lot of choices. Yeah, so please list out the path. You can list out the vertices of the path. I will write the path for you. Yeah, sorry, P. Slightly louder, P4, P4, P3 and P2, right. So her chosen path is this, that is P4, P3, P2. So I will call this path as some T1 path now, okay. Is there any other path somebody wants to suggest? We will see what happens with this path. Now I will let people volunteer rather than me volunteering people. Yes. P5, P7 and P9, okay. So good. P5, P7, P8 was the old path, so I will not agree with that path, okay. So there is another path T2 which is a yellow path, and which is P5, P7, P9, right, that is what you suggested, okay. Okay, so let us take, then this I will call as T2. Now let us look at the path T1. So what does this path T1 give us? So let's try this technique. You suggested that path T1, right? So what do we want to do with this path T1? We want to again apply that path T1. So we want to take M, we may come with M double prime, which is equal to M dot T1, and we will come with some M tilde which is equal to, okay, M tilde which is equal to M dot T2, right. We have another part T2. So our goal is this, and what is our goal? Our goal is to come up with a matching which is popular, and therefore this term switching graph says that you can switch along some paths and we will see cycles to get another matching which is popular. So let us see whether we can use T1. Are all paths good? So how do we use T1? Is it possible to use T1? So one should observe that the path should end at a post which is free, right? Because unless you have something to start your changes, you cannot start your changes at a post which is already filled. So you cannot take the applicant who is matched to P3 and match him to P4 because P4 is already occupied by A4. So unless you move A4 out, you cannot start that path. Okay, this is one issue with the path. So what is the way to correct this path? Include P5, right? Include that P5. So we can do that as well. Is there another issue with this path? If you apply only this path, then yes, if you include P5, then you will apply this path, but then P2 will become a sink vertex, but that is not allowed because we have that every popular matching should match every red post, right? Therefore, the paths must certainly end at a sink vertex, but where should they start? They should start at a non-red post or an S post, right? So now it is very clear. I can take any S post, I can simply take the unique path because as soon as I pick a post, there is one outgoing edge, follow that edge, go to that vertex, there is one outgoing edge. Keep doing this, you must reach a sink vertex because you are the sink component. So if you start with an S post, you will follow a very simple path which is the path that is the only path that is there and reach a sink post, a sink vertex, apply that path, get another matching, and because of this, the way this graph is drawn, we know that applying this path will always give us a popular matching, right? So one very nice property about this graph is also that you can count very easily how many popular matchings are there, right? Because you can simply get all popular matchings by simply applying paths starting at the current matching. And how many paths are there? Once I pick an S post, are there multiple paths? There is only one path because I have one outgoing edge. Once I reach another vertex, I have the next outgoing edge, and that's all, and it reaches the sink. So as many S posts are there here, those many paths I have in this component. Of course, there can be multiple components, but I do it for each of these components, right? So I can very easily count the number of popular matchings. I have not given a complete algorithm. You should think about how many popular matchings are there and how do you identify them from the switching graph. It's not clear from the original instance because you cannot just count S posts of the original instance and say that there are, but once you have the structure of this switching graph, then you can count. So one question that I will leave is, give an efficient algorithm to count the number of popular matchings. And at this point I must mention that these counting problems are not typically easy. One does not have good efficient algorithms for counting problems in general. Therefore, that it exists in this setting is something which is surprising. Right? Okay, so given this you can think of offline. But now that we understand this structure, what can you say about our original question? What can we, okay, so this is about this component of the tree component. What can we do in cycle component? So suppose I have a cycle component which looks again complicated. Remember, again cycles are of even length. Yeah, and there can be other things coming in. So if this is the way the component looks like, can I do any switches? Or is it that everybody in the cycle component is fixed, they cannot move? So let me label again so that it becomes easy for you to talk about it. This is A1, A2, A3, A4, A5, A6. The edges are labeled, okay? A7, A8, A9, A10. So is it the case that if I have just this as my switching graph of my popular matchings instance, then I cannot compute any other, I do not have any other popular matching in the instance. So there is a cycle, right? Along that cycle, you can apply, actually you can apply that cycle now. So instead of applying any path, because if you take a path, there is no way to apply that path. If I start with A1, A2, A3, A4, A5, A6, I do not have a free post, right? So if I do this, it means that I will match A2 to this post as well as A6 to this post, which is not allowed. But in the cycle, I can do the switch. Therefore, I can do a switch and then reverse the direction of the cycle, but everybody else doesn't change, right? So if I take the cycle, I can apply that and it will amount to changing the direction of my edges, that's all. The rest of the applicants will remain as it is and I will get another popular matching. Is this okay? Okay, but what about these applicants, the A1, A2? I mean, can I match them to any other post in any popular matching? So the question is, so for example, I can say that A3 is an applicant who sometimes gets matched to its F post, sometimes to its S post, because irrespective of what this post is, the other post is an S post, right? So in some popular matchings, it gets matched to its F post, some to its S post, and so on. This is true for everybody in the cycle. What about A1? Do I have such a flexibility for A1? No, right? Because A1 is an applicant, if you try to switch it, there is nowhere you can switch it, right? So A1, A2, A7, A8, A9, A10 are all applicants which can never be switched from their current partners. So look at their current partners and ask, is its current partner an F post? If it is an F post, this applicant is an AF applicant. If it is an S post, this applicant is an AS applicant. And that's it. You cannot switch this applicant. There is no other popular matching that can match this, this applicant to any other post. On the other hand, everybody that belongs to the cycle can always be switched. Therefore, everybody inside the cycle is an AFS applicant. What can we say about the applicants inside the, in the tree part? So they can always be switched, right? So therefore, all of these are AFS applicants. So take any applicant. If it is okay, what if it is an F post? Yeah, so you should ask, what if it is an F post like this, that is, so P10, the applicant matched to P10, can it be switched? Yeah, does everybody see that there is an applicant which is at P10? So how does that picture look like? So anyway, because it's a simple it's a simple case that it is an applicant which is A10 who has a unique F post which is P10, because if there was somebody else who treats it as its F post, there would be an incoming edge, but that is not there. So this is that applicant, and it can get switched to P8, which is its S post, right? But such an applicant can never switch, because otherwise that matching will not be popular. But what I am saying is, using this switching graph, it is easy to determine whether the applicant is AF or AS or AFS, right? So you just have to ask whether there is a switching path starting at that applicant or that path. A5.